In this episode, we're going to code a digital clock in pure C using Raylib. As you can see here, this is an awesome project for anyone interested in learning C from the ground up, because from an empty source file, we're going to create this digital clock right here. It's a graphical application. You will need to render your own digital clock segments here, your own digits. You will make up the geometry of these segments yourself. We're not going to use a font. We're going to use our brains to render the geometry using so-called triangle strips, which are an interesting concepts to define arbitrary shapes in Raylib and OpenGL. It's super universal and is used in game development everywhere. So there's a lot of stuff to learn. We're also going to learn how to display times, how to deal with times and C, and we're going to tie everything together to this awesome clock. So let's just jump right in and start. The best starting point is always to have a simple file that has the same name as our project. Let's include something and print something to the console just to see that we can compile something. It's always a nice idea to start with hello world, and then we will build from that hello world. And I'm going to cd into that directory here, and inside we have a single file. Let's compile that single file using GCC or even CC just, and if we execute it, then we see hello world. All right, so how do we clockify that code? It's quite simple. We just fetch the current time. So we can fetch the current time using the system library function time. So we have to look up man3 time, and as you can see, this is a function here that returns the current time. We include time.h and it returns, if we pass a null pointer, it just returns the value as a time_t. So let's use that and then store the time in a variable called current time, just like this. We also need to include time.h for that. And then we can print the time and convert it to a string using ctime. Ctime is taking as input a time value, a time t value, and it's returning a formatted character pointer, so a formatted string that we can use to print. So let's just do character pointer time string, and that is ctime of the current time. And then we can print f that the current time is, and then we print a string, new line. Don't forget to put the variable here that we want to print, because I usually forget that, but this time I didn't. And if we compile this now, we still only have a single source file and a single executable. Then we get a warning ctime current time. Right, this is because the ctime function, as you can see here, let's search for it, ctime, there it is, takes as input a constant time t pointer, which we have to adapt in our source code. So this must be the address of current time. And now we should be able to compile this. Right, this time we don't get an error. If we execute this now, we get the current time is, and we get a well-formatted time string. Of course, now if we re-execute it, we get an updated time string. So this is really fetching for us the current time. But this is not good enough for creating a digital clock, right? Because a digital clock has a real... What we want to do is we want to have a graphical overview of everything. We want to have a graphical window that showcases this value, and we don't just want to print the string. This is too boring. We want to really render a real digital clock. We want to simulate a real digital clock with the 7-segment display, just like here. So 7-segment display. So this is exactly what we want to visualize in a graphical user interface. We want to have a graphical 7-segment display such as this one. How do we do it? We use Raylib for our graphics, and setting that up is quite straightforward. We just go to the sample here, to the simplest possible example. This tells us to include raylib.h. Okay, we can do that. Let's try to do it and see if we can still compile it in a second. But to be sure, we must call some method, for example, init window, or maybe even simpler. Maybe it's nicer to, if I look up the functions here, raylib.h, there it is. This is the Raylib header file. And now we init window. This is the first function that we're going to call. Init window takes in as input a width and a height, and the title should be quite simple, right? So now we can do init window, the width, the height, and a window title that is just digital clock. And the height and width, let's define them globally. They are constants, preprocessor macro constants that never change. I usually go with width 900 and height 600. It's just a nice size for a test project. And if we compile this, this won't work because, of course, now I left a syntax error in here. I left the GG down here, which I have to remove. And now let's compile it. And now it's complaining about an undefined reference to init window. That is because we need to link Raylib. In the simplest possible case, we can just do -l Raylib. I'm not sure if this works. Let's just try. And it worked. Okay, so that was good enough. Sometimes you need to link more than just Raylib. It's all documented on Raylib's GitHub page. On, for example, there's something here. We're going to see it later once it's necessary. For example, if you use OpenGL or something, but I don't think we are even going to need that. We just want to initialize a window. And then as an example here, we want to keep the window alive because right now what's happening is that the window is opening and closing immediately. This is not what we want. We want to init a window, and then while the window should not close, we are doing something. So let's just create let's just set up this loop, remove some of the things inside. For example, we don't need to draw text. We can clear the background and make it black. I prefer that to white. And this is now our basic Raylib loop. Let's see. And now we have a black small window. That's perfect. And also note that the title is now digital clock. That's quite nice. Now we can close the window. This is all fine. In the end of this example, there's a close window function, but somehow it doesn't change anything. It still seems to work fine, even if we don't call it. I don't know. I will omit it and let's see if we face any errors. I like to omit things that we don't really need. So how do we get the... Oh wait, let's start with the simplest possible thing to do. We want to eventually have a digital clock in our Raylib window, just like any of those ones, right? So what's the simplest component that we can start with? Well, in the simplest case, we want to just draw anything to the display. For example, a rectangle. But in those examples here, these 7-segment displays, they have these nice shapes that work well together. We might also define those shapes. Let's start with a simple rectangle that we draw to the window first. So going to the Raylib cheat sheet, we can usually find a couple of functions here. This is full. This is loaded with all Raylib functions. I think it's even equivalent to raylib.h. If we draw rectangle, if we search for draw a rectangle, we can also find the same functions here. Maybe it's even the same content as in the raylib.h file. Yeah. All right, so let's draw a rectangle. It takes as input a position X, position Y, width, height, and color. And we can draw a rectangle after clearing the background. So draw rectangle here. Then we specify an X position, for example 50, Y position 50, then a width, let's make it a wide rectangle that has a width of 300, a height, let's make it 20, so a rather thin one, and a color that is ray white. All right, how do I know that ray white exists? It should be in this raylib.h file here. You can see that a couple of colors are predefined. If you don't want to use any of the predefined colors, then you can just define your own one, like this here, C-literal color, and then you pass the structure here with the RGBA values. But now this should be drawing for us a rectangle. All right, this could already be a segment in our digital clock. Right, but a real segment in a digital clock doesn't really look like this. So we have to adapt the shape. Let's open a drawing software so I can draw something for you guys. We probably want to have a shape like this one. This is a classic one. Yeah, but this one has a couple of round edges, so that is unnecessary overhead. Maybe let's use something like this. This is a very good example. It's some sales page here. But I want to have this kind of shape. So what we're going to do is definitely not starting on a white canvas. Then let's go down here. Or maybe like this, like this. Like this. You get the point, okay? This is quite skewed, but I think it's fine. And this is the shape that we want to draw. So we could do this a couple of ways. We could either draw a rectangle first, and then we draw a couple of triangles here. Like this and like this. This would effectively give us this shape down here. But there's a nicer way to accomplish that, and that is using the, let's have a look at the Raylib header file. That is using the draw triangle strip function. What is a triangle strip? A triangle strip is a compound of several subtriangles, and a triangle strip is a very powerful tool to draw any shape that you want. For example, this right here is a triangle strip. It consists of a couple of corners, A, B, C, D, E, F, and as you can see, you define these corners here and their respective coordinates, and from those corners, triangles are generated that are concatenated. So what's happening is you define a couple of points. For example, there's a point here, there's a point here, there's a point here, there's a point here. And then the triangle strip will know, let's say this is the first point, this is the second point, this is the third point. Oh God, this is the third point and this is the fourth point. Then the triangle strip will automatically connect those points in that order, and after every triangle is completed, it's going to connect the triangles back together. So 1, 2, 3, this is the first triangle. Then 3, 4, and then 4 closes back to 2. So every 3 points connect to a triangle, and this is then the resulting triangle strip. Basically, it's a strip of triangles, obviously. All right. So we're going to draw a triangle strip. We define a couple of points and a point count. And then we're going to give this a color, and that's it. So let's try to do something. Draw triangle strip. points count, and the color can be ray blue. And now the points are an array. For example, vector2 points array. What's the size of that array? The array is of size count. I'm not even sure. If we define the array right here, right away, then we maybe don't even need to put the count there. I don't know exactly. And the count is an integer, if I recall correctly, yes. So let's just define 4 points as in the example that I drew here. So count 4 points. So this is a vector of structures now. We could define the points outside of this, points A, B, C, D. Those are our 4 points. And then we do A equals, and then we give this a vector2 value that is just 2 coordinates. So vector2, if we have a look at the type definition here, it's just a floating point x and a floating point y. So let's give this 50-50. And B is 100 and also 100 here. And then C is, again, let's make it 80, 20. I don't really know how that looks like in the end. And then this one can be 200 and Y is, I don't know, 30 maybe. Let's just see which shape this will result in. But this will probably be a very skewed shape with 4 corners. These are our coordinates, and now the points that we put into the array are A, B, C, D, which we have just defined. And the count is now also initialized. It's this up here. Or we could also do size of vector 2 divided by size of points divided by size of vector 2 or something like that to dynamically during compilation time, or rather during pre-processing time, compute that. I think that this is fine as it is right now. So let's try to compile this. Of course it doesn't work. It would be a surprise. Error expected expression before curly brace token in line A, B, C, D, where I initialize. Ray blue also doesn't exist. Sky blue it is. And maybe it's complaining about the fact that I'm not casting this to a vector 2. Maybe this works. Yeah, and this seems to work. So as you can see now it compiles. If we execute it now, we have our white rectangle and we have this triangle strip right here with this point being A, this is probably B, this is C, and this over here is point D. Perfect. This is already an awesome result. So we got the visualization part down, or at least the foundations of it. So now instead of creating the skewed shape here, let's create a real 7-segment display segment. 7-segment display segment. Let's create a real segment that would be part of a 7-segment display. All right. So I'm going to keep the other ones, the other shapes in here just for retaining what we've done so far, but later I'm going to clean it up. So let's create real 7-segment display segment here. And in the end, we're also just going to draw a triangle strip. Now we just have to define 7 points that we want to draw we're going to use the same approach as here. It's just going to be 7 points that we're going to draw. So the count is going to be 7. It's going to consist of 7 points that we are going to define here. A, B, C, D, E, F, G. So for a better visual help here, I'm going to draw them here. Where's this damn paintbrush? Here it is. Okay, so this is point A, B, C, D, E, F. Okay, we're going to only need 6 points, and then they're going to connect together. So 7 segments require only 6 points. And why do they only require those 6 points? Because once we connect them, as you can see here, these are going to connect together like this. These are going to connect together like this. These are 2 lines, and then we're going to connect back like this. Then we're going to continue to connect over here, and then these 2 are going to connect back like this. And then we're going to connect down here. Then these 2 are going to connect back like this. And then we need just one more connection to the last point, and then this is going to connect back like this. And this has defined the whole shape then. Alrighty, so let's try to do it. How do we define a real 7-segment display? Well, we want to be able eventually to define multiple 7-segment segments that are also arranged like this. Oh my god. Like this and like this. Basically, we have these 2 variants here. The vertical one and the horizontal one. They are similar, but we probably need handling for each of those. We just want to create the first one, and this is the horizontal one first. How do we create a horizontal one first? Well, what parameters do we need? We need 2 parameters. One is the fact that it's horizontal. Okay, it's going to be implicit now. And or maybe we're going to need the center point of this segment here. This is the center point. This is a variable we need. And maybe the width of the entire segment. Or the width of... actually the center... Whoops. Actually the center point is required. And the width and the thickness of this segment can be hard-coded. So let's just assume for now that we have a center point. The center point is a float. Center equals, let's just put it at the center of the screen. And of course the center point consists of x and y. So it's going to be a vector 2 that is the center coordinate. Vector 2 center is equal to width divided by 2 and height divided by 2. This is going to put the rectangle at the center of the screen. And then the first point, A, is in relation to the center point. It's the center x minus... Oh my god. Assume that all of this down here is the width. Then this distance is width divided by 2. And then this is another variable that we're going to define. Maybe it's the thickness. Okay, so this is going to be center.x minus segment or seg width. We're going to define a variable for that. float segment width equals 200. Let's make it 200 for now. Minus segment width divided by 2 minus, and then we need a segment thickness. And the segment thickness is, for example, 50. Yeah. Do we need to divide the segment thickness by 2 as well? Yes, if we assume that the thickness is going to be the cross section of the entire segment, and we want to reuse the thickness here and here and here, and those should be equal. Yeah, okay. Let's also put segment thickness divided by 2 here. This should be the x-coordinate of the A point, and then we need a y-coordinate of the A point, and the y-coordinate of the A point is the same as the center point's y-coordinate, center.y, right? Because the A point and the center, they reside on the same vertical axis, on the same horizontal axis. Okay, then let's do the same thing for B. Point B is this point up here. So center x minus segment width divided by 2 and center dot y minus segment thickness divided by 2. Right, because now we need to move from the center y also up a bit. Remember that in screen coordinates, an increment in y is moving down. So that's why we have to do minus here. Then point C. C is this point down here in this corner. It's going to be very similar. Center x minus segment width divided by 2. And center y, but this time plus segment thickness divided by 2. All right, I think this might be going very well so far. Point D. Point D is this point over here. And this should now be simple, guys. If you want to try it, then stop the video now and try it and then resume yourself. All right, point D is center.x plus segment width divided by 2, and then center y minus segment thickness divided by 2, again because it's moving up relative to the center point. Then E is segment, this is the same thing, it's just moving down again. And then F is the same thing, but no, it's not the same thing. It's moving to the right once more. So we need to add the segment thickness here divided by 2 in the x-coordinate, and the y-coordinate is the same as the center point y-coordinate. All right. And then here in the points array, we define the points A, B, C, D, E, F. Those are the complete set of points. Wait, where's my project? Digital clock, here it is. And now here, if we compile this, I think it might already work. Let's see. No, it doesn't work. There's an error in there. What's the error? Error D, redeclaration of D with no linkage. Oh, of course, we have colliding variable names here. This is not so good. But actually this is not good. It's not a good practice, but of course. No, I'm redefining those because I'm redeclaring the data type. Okay, for that we can just remove the original rectangle that we have, the original triangle strip that we have used. So let's compile. This worked, and now we see nothing. Oh, damn it, why doesn't it work? We are defining our triangle strip here. We are drawing it in sky blue. These are the points. compile it properly and execute it. Yes, somehow it doesn't appear. Why? Maybe I need to enable all warnings just to be sure on the compiler, but this doesn't change anything. A, B, C, D, E, F, those are the points. The count is 6. The center is this. Segment width is this. Segment thickness is this. All of this might be fine. But maybe I have chosen the values just so that something doesn't really add up here. So what if I do 400 just for testing? No, of course I need to compile first and then execute. No, this doesn't work. Why? I'm also not seeing any error here. So I think this is an opportunity for us to jump in the debugger and see the value of the triangle strip that we have defined down here. So to do that, we have to jump in the compiler first, define -g for the debug flag. Of course, I introduce a typo now, and now we can call the GDB debugger on our executable, layout source to see the source code, and now we can go down here and put a breakpoint in line 36. This is the interesting line. And then we run this. Then we refresh our display and print points. And these are the points that we have defined, and they look good on first glance. So why is draw triangle strip not drawing anything? So the first point is this. The second point is this. This is another point. This makes sense on first glance. Then we move up. So we keep the x coordinate the same. The y coordinate increases in this case. Is this correct? Wait. Maybe. Wait, on the first point. This is the first point. The second point is this one up here. Okay, so in that case, on the second point, the y coordinate must decrease. That makes sense. Then on the third point, the y coordinate increases again. All of this looks fine on first glance. Probably there's some super obvious issue that I'm just not seeing right now. Draw triangle strip. Then let's have a look at the documentation here. So we pass a vector to points with a point count and a color. This is exactly what we're doing here. The array is essentially a pointer, then a count, and then a color. Sky blue. Wait, is sky blue really defined in Raylib? Sky blue. It is really defined. It is there. What if we make it ray white? Just to be sure we use a color that definitely works. It's not there. Is my rectangle off screen? My shape, I mean. No, I can't imagine that it's off screen. But the center point, I have defined the center point as width divided by 2 and height divided by 2. This makes sense, right? And all of the variables, they seem reasonable. Break in line 36, run. Refresh. Points count ray white. Print points. Next. Do we need to maybe limit the frames per second? Because we can set a target frames per second here, because currently we're running at maximum frames per second that are possible. So that's probably thousands of frames per second. And maybe Right after drawing this, the screen is immediately wiped here in clear background and the result is never visible to us. That could be the case actually. So we could do set target FPS. I'm not really sure if that's really the solution, but I mean, we can just eradicate it. Frames per second. Let's quit this. Let's recompile and run it. And that's still not it. We compile. Are we using any weird data types? Maybe. The count is an integer. The center coordinate. The center coordinate is this. Yeah, we definitely have to use floating point numbers, not integers. Maybe because our center, I'm not sure. If we use integers here, which we are doing for width and height, the vector 2 should still contain floating point numbers, right? Let's go into the debugger and check the types of all the variables. Break in line 36, then run, then refresh. And now let's do what is center is a vector 2. Okay. What is center.x? It's a float. Okay, so that seems to be working. Then if we go into the next line, what is points? It's a vector 2 of size 6. Yeah, it has 6 entries. That's right. What is points at index 0? Vector 2. Okay. And then x, it's also a float. So they seem to be properly cast. And the values in those segments are also reasonable, because if we do print points, then we get real, reasonable values in here. Print count, count is 6. But for some reason, this up here worked. Why? If we compile this, wait, if we remove this down here, if I remove this down here, and I compile the code, oops, cd digital clock, I compile the code and I execute it. This works. Why does this work, but the code below doesn't work? It's the very same thing. We define vector 2s and we draw the points. Then we draw the triangle strip down there, points, count, sky blue. Maybe I'm missing something. I'm definitely missing something. This is all of our current code. We draw the rectangle here. Then we do all of this. Then we draw the triangle strip. Let's re-add the set target frames per second to 60. But this doesn't make a difference. Why? So, there must be some stupid reason and I'm just not catching it, guys. Break, 36, run. layout source, print points. The coordinates, they totally make sense. The coordinates are all on screen and they all make sense to me. But they can't, probably then the issue is just in the points because something is wrong there. $325, 300. This makes sense. 350. Okay. 275. So this is the corner up. Then we go down again. 350. Then we go to the... Yeah, we go down. Then we go to the top right corner, to this D corner here. That's this coordinate. And then we specify this coordinate. This is also correct. And then the last coordinate is this one. 575 and 300. They all look correct to me. What if I remove the draw rectangle? What if I just increase the count? And let's see what happens then. Wait, why is this printing something now? And why is it looking so weird? So changing the count apparently changes something. What if I change the count to 5? This is odd. This definitely means that it's all my fault. Count 7. This is completely broken here. This looks like a triangle is created, and this looks like it could be the side that we have defined, the last side, and then this side is moving to the 7th point, which we haven't defined, which contains 0 in memory, which is this origin here, and that's why this last shape is appearing like that. However, I still don't get why the rest of our shape points are not rendered. So it seems to be the case that the last segment is rendered in combination with this origin. Am I maybe misunderstanding something significant about the triangle strips? What if I just do A, C, B, D, F, E? I reduce the count to 6. And then compile and execute it, and this seems to be almost working. As you can see, this is the shape of our segment. I still don't exactly get why. What is the order in which we have to define the points? OpenGL has built-in support for triangle strips. Fixed function. Maybe we're using OpenGL. Are we using OpenGL? It seems to be the case that the points are defined in clock order here. One, two, three. But no. Note that only one additional vertex is needed to draw the second triangle. In OpenGL, the order in which the vertices are specified is important so that surface normals are consistent. In OpenGL, the order in which the vertices are specified is important, such that the surface normals are consistent. So maybe conceptually the order of points is not important, but in OpenGL it is important, and Raylib uses OpenGL. So this always starts with V0 here, V1 there, V2 here, and they seem to always be defined in this order, although I don't get here. So here V0 comes before V1, comes before V2, but then how does V3 connect in that order? It doesn't. V3 in this rotational order here comes after V1, as you can see. Huh? The ordering is to ensure that the triangles are all drawn with the same orientation so that the strip can correctly form part of a surface. So I'm doing this, and I'm doing this. I'm doing this, then... No. Something in here must be... Wait. Triangle strip, order. Yeah, this is primitive drawing. This is the approach I have taken. Primitive drawing. 0, 1, 2, 3, 4, 5, 6, 7. And I've been doing A, B, C, D, E, F. So conceptually it should be correct. A, B, C. So B must be center minus segment width divided by 2. And center Y minus segment thickness. That's correct. Center X minus segment width divided by 2 and center Y plus segment thickness divided by 2. In the diagram above, the vertex would be V1, V2, V3 for the first triangle. V1, V2, V3, V4, V5, V6, V7. That's exactly what we're doing. But is that maybe a wrong example? No. A, B, C, D, E, F. I see on Stack Overflow some people arguing about the order of the points for the triangles that we have to define. And here, some say that the order is irrelevant, but there is somehow the common notion everywhere where I look it up that the triangles should be specified in counterclockwise order, especially also... No, but in this example, it's not counterclockwise order, so I don't really get it. But this is just general geometry here. This is not OpenGL. So maybe in OpenGL, it must be counterclockwise order, which we are not doing because here we are doing A, B, C. In this order, this is clockwise. So probably we can just reverse the order. The simplest possible thing that we can do is just state ACB. ACB, this is counterclockwise. Then EDF. EDF. And let's see if this changes anything. Okay, that's it. I spent so much time researching this, guys. That's ridiculous. So the rotational order in which you specify the points of this segment matters. It's not... Even though purely from a mathematics perspective, it doesn't matter. It matters from a OpenGL perspective because this is rendered by OpenGL and OpenGL seems to be sensitive to the order of all of this. So I would say now that we have figured this out, let's make the color ray white. And this is now our code that renders a simple segment. since we want to create a digital clock, we need several such segments. And this is now the opportunity to create a function that renders these segments for us. So I would say let's create a function up here that does not need to return anything, and it can be a function that is called create segment or draw segment. It takes as input. We will figure that out in a second, what it needs as an input, but likely just center coordinate. And what else? The center coordinate, and the rest can be hard-coded globally. The count is also always the same. The center coordinate can be a vector to input coordinate here, center. Then the segment width and thickness, they can be global constants. We can also define them. It really doesn't matter that much. And then we draw a segment here. Let's see if this works. If we put it in the method, the center coordinate is a vector. Or is just a structure actually. Let's say 300, 200. Let's say if this works. I don't even know if we can just pass structures anonymously like this and in C. No, we apparently can't. Maybe we have to pass also or cast this structure also. And now it probably works. No, it doesn't. Okay, it doesn't want to do that. The center coordinate is a vector 2 center. It's equal to 300, 200, and that's the center for the segment. No, or is there a different error? Ah, of course, there's an error up here. That was the error, so probably passing the structure directly should have worked. Now this doesn't work. Why doesn't this work? Because for some reason I reversed this order here again. A, C, B. Did I undo something? A, C, B, E, D, F. E, D, F. And let's try to compile this and execute. And you see that the segment is being rendered. Perfect. Okay. As a next step, we need a way to draw multiple segments. So let's draw a digit. Do we draw a digit? Let's draw a digit. Yeah, we draw a full digit, or rather we draw a vertical segment first. Maybe we need to put a Boolean here, horizontal. And if it's a horizontal segment, then we draw this. Then these are our points. Then these are the points. And the definition can be, the declaration can also be done outside of the if else. Else if it's a vertical segment, then we define different points. So in the same fashion, let's also define vertical points here. Now I have to be careful because here the points are defined in A, C, B, E, D, F order. So how would I have to define a vertical segment? I would say that we can do it in the same order like this, A, B, C. Now I think I need to fix up the order of the horizontal case first, because otherwise I cannot rely on a mixed up point order down here. So let's put A, B, C, D, E, F here. And then in here we need to mix them up. This was C, this was B. And about the others, I don't really remember. A, C, B, E, D, F, E, D, F, and now we can rearrange them here like this, such that they are in alphabetical order again. A, B, C, D, E, F. Maybe. Okay. Now we draw a segment that is horizontal. So we put a true here and include standard bool for true and false. Compile, this renders the segment. So this seems to be working. This is okay. This is actually very good. It works. And in the other case, in the vertical case, now we need to adapt the variables here. I think we can do it like this. A first, then B here, then C, D, E, F. So let's do that. Center X minus, so the X coordinate is first the center X axis here. This does not require anything else in the X component. The Y coordinate is segment is center.y minus segment width divided by 2. Actually, the width should be called length in this case. But okay, we use the same variable. Segment thickness divided by 2. This is A. Then center X is center X minus segment width divided by 2. Center Y minus segment thickness divided by segment X minus segment thickness divided by 2. Center Y is, or the Y coordinate is center Y minus center segment width divided by 2. Then center X. Now it's correctly shaped. It's still flickering. Why is it flickering, guys? Can we not use the same vector 2 here? That's the only thing that's shared between both draw calls, vector 2, other center. That doesn't make sense at all to me. If horizontal, then we do this. Else we do something else. We pass the Boolean value true or false. Draw segment other center is here. Where does the flickering come from potentially? It does not make any sense at all. The center is not shared. Those are two separate segments. What if I remove the first segment and just draw the second one? Now it's stable. That's weird. Why is it stable? Okay. We draw one segment, then we draw another segment. How can the other segment potentially conflict with the first one? Oh, because end drawing is called here. Of course, end drawing is called inside this function, and then end drawing is called twice. That is potentially harmful. Now we've got two stable triangle strips. Oh my god. Okay, this looks good now. Now we just need to properly position the triangle strips. So let's create a full digit, void draw digit. And a digit consists of, at first, nothing. Let's just position all the triangle strips that we can possibly create. So we want the following setup. We want one triangle strip here. Let's just change the color. One triangle strip here. Then one there, one there, one there, one there, one there, one there. This one is the first one, this is the second one, this is the third one, the fourth one, the fifth one, the sixth one, and the seventh one. And let's just place the first one at first. So we can just do draw first strip. What's the center coordinate of that first strip? It's, right, we have to give this a global center coordinate. Vector 2, center. And then we draw the first strip. Where do we draw it? We draw it at position vector 2 first is center. The x coordinate is actually the same as in the original center, but the y is offset up. Center.y minus, and then we move this up according to the segment width, I would say. Segment width. And then we do the same for the second. The second has a center coordinate. Well, we of course need to call the draw function, draw segment. First, it's horizontal, true. Then we draw the second. The second is vertical, so this is not true, this is false. The coordinate is center x minus segment width divided by 2. Of course, this up here must also be divided by 2. But here the y coordinate is also offset by segment width. Segment width divided by 2. Let's just see and verify that we can draw those two. So we currently draw nothing. Now we draw a digit at a specific coordinate, vector 2. Let's just put it at 400 by 400, roughly at the center of the screen. And I think this still doesn't work. Oh, it does work. Okay, so it does do something, it's just not correct. So now we want the first one to be positioned up there and the second one to be positioned here. And the second one looks positioned correctly, the other one doesn't. The first one is positioned at center x, that's fine, and then the center y is offset by the segment width. Is that correct? Segment width divided by 2. It might be correct, although it cannot be, otherwise I would have a reasonable result. Center x is kept. The center y is moved up. What if we just do segment width here, just for playing around? I don't think this will work, but this seems to match exactly. Why? Why? Segment width. Of course, yeah, from the center coordinate, from the center y coordinate, we have to move up a full y step. Okay. Then let's draw the other segments as well. So let me just create the other ones. I think I will speed this up such that it's not boring for you. third. All right, now we have a working digit here. As you can see, we just need to position it properly in the center. And this is, of course, not default of this draw digit method. We just need to pass a proper center into this method, such as the center of the screen. So let's pass a vector to right at the screen's center, width divided by 2 and height divided by 2 in there, and see how that is being handled. And as you can see, now we have a digit right at the center of the screen, and this is a 7-segment digit. And now, of course, this is just the background part of the digit. We want to highlight the individual segments. So that means we need to extend the method drawDigit to draw a specific number. How do we do it? Well, I would say we give it the position as an input, and we give it the number that we want to draw, right? Does that make sense? We want to draw the position and the number. I think that might make sense. Or we create yet another abstraction level that already creates a clock, and then we set the numbers on the clock structure. I'm not so sure about that. We can keep it simple and draw just the digits. So we draw digit. Let's just say we want to draw the 9. Okay, this is the letter 9. The number 9. So this is going to be an integer that we pass into drawDigit int number or digit. And depending on the number that we pass in here, we want to draw the segments at specific colors. Oh, how do we do that? Well, we can somehow define the color per segment here. So this is the first segment, this is the second, the third, the fourth, the fifth, the sixth, the seventh. I think this can be either an array of colors per segment. We can define something like an integer array here. Integer array of arrays, maybe. Digits. That is an array of arrays. And it takes as input, let's say, the values for the number 0. For the number 0, the segment 1 is turned on, 2 is turned on, 3 is turned on, 4 is not turned on, 5, 6, 7. So all the numbers except the 4 are turned on. So what we could do is we could do this. 1, 2, 3, 4 is off, 5, 6, 7. Yes, we can also do this in binary, of course, but in binary we would have to deal with the bit shifting somehow. I mean, this is quite nice. Well, I mean, we could also do, of course, 0b, 1, 2, 3, 4, 5, 6, but then we would need to pad it also to the 8th digit, because a byte contains 8 bits. I find this is the simpler approach, guys. So this is the digit 0. Let's create digit 1. The 1 is, what is turned on in the 1? In the 1, only 3 and 6 are turned on. So let's do 1, 2, 3, 4, 5, 6, 7. That's it. Okay. Now the 2. In the 2, the numbers 1, 3, 4, 5, 7 are turned on. 1, 2, 3, 4. 4, 5, 6 is turned on. No, it's not turned on. 5 is turned on and 7 is turned. I need to redo this one. That was too confusing. 1, 3, 4, 5, 7. 1, 3, 4, 5, 7. Digit 2. Digit 1. Then the next one. 3. Which segments need to be turned on? Segment 1, 3, 4, 6, 7. 1, 3, 4, 6, 7. 1, 3, 4, 6, 7. Okay. That is digit 3. Digit 4. Let's see, digit 4. 2, 4, 3. No, 2, 3, 4, 6. 2, 3, 4, 6. Digit 4. Let's do digit 5. 1, 2, 4, 6, 7. 1, 2, 4, 6, 7. The 6. 1, 2, 4, 5, 6, 7. 1, 2, 4, 5, 6, 7. 7. 7 should be 1, 3, 6. 1, 3, 6. And 8 should be all of them turned on. So this is nice. We can just turn all of them on. Let's do that. Okay. And then digit 9. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 6, 7. Okay, that's our definition of all the digit guys. All the digits guys. This is an array of arrays. Now we want to draw a number. And we can use this digit matrix to look up how to draw a number. So when we draw a digit, we give this a digit value. Then we need to find out which segments to draw in which color. For example, we can fetch the digit segments from the digits matrix. It's equal to digits at index digit minus 1. Because if we pass the 9, then this no, it starts at 0. No, so it can be it's digits at the given digit. It's basically a lookup table. So then we have the digit segments, and then we draw a segment with a given color. How do we draw a segment with a given color? We pass here the color, and down here when we draw the triangle strip, we just specify the color that we want to draw. So now we can do digit segments, digits, draw a segment. What's the color? We ask digit segments, at the first strip, so index 0, is it value 1? If yes, is it value 1? Is it true or false? Wait, what is true-ish and false-ish in C? In the ternary operator C. Provides a shorthand way to perform a conditional assignment or expression. It's taking, I think we will have to do it like this. If it's 1, then this will evaluate the first statement. Then the color is on color. Otherwise, it's off color. Wow. And we can actually define a function for that. Color get segment color for segment no, let's not overcomplicate it. So here we want to append the same statements everywhere. And that might be it. So now for every single segment, we're checking which color should that segment be. Is it on or off? And of course, we have to define the on and off color. So let's do that up here. Define on color is red. And maybe it makes sense to look up the colors that are available here because I like the pre-installed colors. Is there a red even? There's red, yes, red. Here it is. And define off color, and the off color is just a gray. Gray, dark gray, dark gray. Let's pick dark gray. Okay. If we compile this, of course, it doesn't work. I would be surprised if it would have worked out of the box like this. So array type has incomplete element type, integer array digits. Why is it wrong? Has incomplete element type. Does it need the size of the array right away here? I don't know. What if we compile this with GCC? Okay, it gives us the same error. I thought maybe it's some compiler compatibility thing because variable array sizes are not always working, but I think the issue is that I'm missing a semicolon here. Right, so this fixed the issues down here, and there's still the error array type has incomplete element type. This digits is an array of arrays. Declaration of digits as multidimensional array must have bounds for all dimensions except the first. So that's a limitation of variable size arrays, I think. So the first dimension is, I think, the last bracket here. So we need to pass in the size. We have 10 digits. Maybe this works, 10 digits, because we're counting from 0 to 9. Is that it? No, that's not it. But we can actually define no, this is the 10. Does that work? No. And if we define here that we have 7 segments per digit, does that work? Warning: access elements in array initializer. Access elements in array initializer int digits. We have an array that has size 10 because we have 10 digits, and each digit inside is stored as a 7 segment array. Invalid initializer, digit. Invalid initializer digits. In function draw digits. Here digits. I'm accessing the digit. Okay. Maybe I'm mixing up the dimensions here. I thought the outer one is the outer one in this initialization as well. What if I do 10.7? Maybe that works. If it works, then I have just mixed it up. This is not an initializer. This is, I just want to get from the digits array or the first row basically. From the digits matrix, I want to get the first row. Can I not do it like this? Do I maybe just need to put a pointer here? If I just get an integer pointer, digit, segments. Oh, this is probably not a good practice to do. But it seems to work, okay. It seems to partly work, at least. So we're drawing horizontal segments here. And now the issue that I'm trying to solve is this overlap here. We could pull all the segments apart, yes. Is that a good solution? I don't know. We can just do center y plus 20 or something. I know we just defined an offset. Then we defined an offset here. Plus. No, wait. Do we need to move all the coordinates up? Yes, I think we do have to do this. But then for horizontal segments that are positioned at the bottom of the screen, then we would need to pull them down. No, that's not it. Maybe we can change the center point that we pass into the draw segment. So center y is modified here. The first segment can be here, and then let's just do minus offset to move it up a bit. The second segment doesn't need to be changed. The third doesn't need to be changed, maybe. Or maybe it does need to be changed by a bit. But let's just move the first and the seventh segment up and down respectively. Let's see what happens. Okay, this is okay. This is fine. This is good. So, right, that's a good solution. We just need to move. We just need to move some segments apart. So here we do minus offset, and then on the second we do minus maybe offset divided by 2 to move this apart also a bit. Same for the third. The third segment is this one. These are the second and third segments. The fourth can stay in place, and then the fifth and sixth need to be moved down. So we do fifth and sixth segment width plus offset divided by 2. Same thing down here. And the seventh can, yeah, we have already modified that one. This is looking okay-ish. Yeah, we just need to adapt. What do we need to adapt? We also need to apply the offset to the x-axis. Yeah, we also need to apply the offset to the x-axis. So let's start with the first segment. Here the X is centered, so we don't do anything. I mean, it's located right here, so this doesn't need to be changed. The second one needs to be pulled there. The second one needs to be pulled apart in this direction. The third one needs to be pulled apart in this direction. So let's do center X minus segment width divided by 2 minus offset divided by 2 or minus offset. Let's just keep minus offset for now. Or minus offset divided by 2. I can't imagine they need to be offset by that much. Same thing for the third, but there we need to do plus offset divided by 2. Then the fourth needs to be pulled left just like the second one. No, the fifth needs to be pulled apart just like the second one. So let's do minus offset divided by 2. And same for the sixth, which needs to be plus offset divided by 2. And this looks already quite nice, although they are now too neatly aligned for my taste. So let's increase the offset a bit. Offset and make it 67. This looks very good. Oh, awesome. Guys, I was so close to giving up this project because it was so sickening to deal with all the geometry. I hate this. Or, well, I hate it in a sense, but I love it when it works. This is now perfect. This is now a digit. Okay. I would say we can adapt the segment width. And maybe the offset should be dependent on the segment width, because if we reduce the size now to, let's say, 150, let's see how that looks like. Of course, don't forget the semicolon. Ah, no, it looks fine. Wait, let's just reduce the size a bit more because we need to squeeze in a couple of more digits. This looks okay. The thickness is quite high. But we all love good thickness. That's okay-ish. So I would say we can keep the thickness and the width independent of each other. Let's make it quite thick, but not too thick. That's good. The offset, we can adapt that to 42 maybe. No, that's too little. But this looks quite elegant to have this single pixel space here. What if I do 50? That's something that we can work with. Although it should be a bit smaller. It should be a bit smaller. The width should be a bit smaller even. That's, what was it before? 80. Let's make it 60. Okay, let's reduce the thickness to 33. Okay, and now 25. Nah. No. That's not what we want. Should be quite thick and quite large. I mean, it must be present on the screen. Okay, let's just see. We will adapt it later. Now the next task is to create multiple such numbers on the screen, because we don't want to just draw a single digit. We want to draw a time, right? So let's create a function draw time, and take as input a current time maybe. And then inside draw time, which we call here now, don't forget it, we draw the current time. Inside draw time, we draw a digit. Okay, and now we should have the same result as before because we just extracted this digit into a separate method. And now we can draw a couple of digits. So the first two digits are the hours. So let's define a space or digit distance I would say that can start with, well, since a segment is already has a width of 60, maybe the digit distance should be at least 100. And then we can go down here and modify the x coordinate to be let's just put it at, yeah, how do we position the 4 digits properly? We need to do something like width divided by 2, that's fine, minus how many digits do we expect? We expect hours, minutes, seconds. The minutes should be at the center. The hour should be, yeah, we can just guess this. I mean, that's probably fine. But it's not as elegant. Width divided by 2 minus, let's just make minus 4 times the digit distance. And then the next digit is the same thing, but 3 times the digit distance. And we draw another digit such as 3 just for experiment. And let's see. Okay, now we see that we have 2 digits here, and they are wrong, but they are wrongly rendered, and we need to change the digit distance apparently, because somehow it's very low. I don't get why. Now they are not visible. Am I using a segment width that I have not defined globally somewhere? Digit distance is this. But that's actually the distance between the digits. Let's create a start x. And then a digit distance, that's this. And then down here we can just simplify everything. Instead of deriving everything from the center x coordinate, let's just start at start x. For the first digit, the second one has starting coordinate start x plus the digit distance. Okay, I think we need to increase the digit distance a bit. 200. Okay, it can be a bit closer. 140 maybe. No, that's too close. 170. Okay, I go with that. That's fine. So now we have 2 digits on screen. Perfect. That's already approaching something nice here. Then start x plus twice the digit distance and plus thrice the digit distance, and then we do it yet another time, plus 4 times digit distance and 5 times digit distance, and the seconds, no, the millisecond, no, that's the second one, seconds hand, not milliseconds. We're ignoring milliseconds in this video. All right, I think it looks like our digital clock is fitting only this many digits. So we could either redefine all these variables here to be relative to the width and height of the window. That would be possible. Or we could just say we increase the width and height of the window. Let's try and see what this looks like. All right. If we change it to 1100, how does this look like? That's fine. It's not so elegant. Okay, maybe how can we do width 900? Offset is, let's say, width divided by 10. So it starts at the first 10%. Oh no, starting x can be width divided by 10. Then the offset can be I don't know what. The digit distance can be width divided by, I don't know, 6. Then the segment width is width divided by, how many digits will we have on the screen? We will have 6 digits, hours, minutes, seconds, and then colons in between those. So maybe we need to do divided by 8. Not so sure about that one. The digit distance is a bit small. That's a bit big. Width divided by 4. That's okay. And then the thickness can be width divided by 20. That's okay. And the offset can be width divided by 20 as well. All right, and now let's change this a bit. So now we are really defining everything in relation to the screen's width. But I don't like that somehow. Somehow it's weird to do this. How about just hard coding it? Hard coding it is much better. I mean, this looks awesome. I just need to fit in the other digits. Okay, let's just increase the size of this. That's a bit too narrow. Okay, and then so this looks quite okay. We just need to put in colons between the digits now. And why do we only render 9s? That's also weird, because I'm printing 3s as well here. So this is a 3, this is a 3, and this is a 3. So I would expect 3s. And these, no, there are 3s. Okay, this is a 9, 3, 9, 3. It's really hard for my eyes to recognize this somehow. It looks like it's all 9s, but it's not. Okay, we need to fit the colons as well. So here we need to draw a colon at a specific position, start x plus digit distance, multiplied by 2, height divided by 2. Times the digit distance. We draw a colon at a specific coordinate. So what's the input here? And then digit, we remove that. How do we draw a colon? We just draw circles using Raylib. Here, draw circle, center x, center y. Draw circle. The center position can be passed as a vector using draw circle v here. Center is a vector 2. So vector 2 center dot x, center dot y minus, let's move the first column up a bit. Let's say minus 50. And then we need to pass in the radius of the circle. Let's make it 25. Or let's create a colon radius global constant. Define colon radius is 25. And now I think it's also time to find all segment width occurrences and redefine them to a global constant. Segment width is this. What? Okay. This must be a define statement. Then we remove the equal sign, the assignment. And then let's do the same for the segment thickness. Segment. Now, segment thickness. This can also be a global constant. Segment thickness, what's the point? Just to align with the other variables, because mixing up global variables for constants and then these define statements, it's somehow not so nice. Either just decide for one single approach here. Okay, and now in the draw colon function, where is it? Did I just undo it? Ah no, I just didn't call it draw colon. Now it exists. We use the colon radius and the color is the same as the on color. Perfect. Now if we compile and execute, this doesn't work due to what? Define start x is 100. Wait, let me just remove everything and let's check the errors again. Incompatible type. Ah, okay, I see. I left in the semicolons here and here, and this should now be resolved, at least in part. Too few arguments to function draw circle. Draw circle in line 88. 88 here, draw circle takes as input the vector 2, the radius and the color. What else? Vector 2, radius, color. Why does it think we don't pass enough arguments that I don't know? Probably I'm messing up somewhere. Ah, of course, I need to pass a single vector 2 here. Vector 2. So now what error remains? Incompatible type for argument 1 of draw circle. Right, because we don't use draw circle, we use draw circle v to draw a vector. And now this works, and we are rendering a single circle, a single column in here, as you can see. Now let's render also the other one. As you can see, now we have a second one. Now what's remaining is to move away the other digits here. And put another colon after the fourth one. After the fourth position, I mean. So maybe that's it. Okay, the colon distance is somehow, I really don't like it that much. But it's equivalent distance between all the characters, but we could adapt it, of course. But currently a colon takes in as much input as a full digit. That is not technically necessary, but it's okay. Maybe we will judge this once we have shrunk down the entire segment a bit. So let's make this 40. Okay, and now we can reduce the digit distance accordingly. For example, 120. Yeah, almost. We can increase this a bit again, 130 maybe. All right. That's okay for me. What do you think? That's okay, isn't it? That's fine. What if we do 135? And the width, the thickness can be a bit smaller. I know, guys. Sorry. But this looks too spacey. No. Then let's reset this to 130. Keep this. Reduce the column radius to 15 maybe. That's too little. My artistic eye is telling me that. That fits together quite well. So what we do is we always draw a start. We always have a starting x coordinate here. Let's say that the starting x is start x and it starts at start x. Then we can replace that with start x. And then we know that the next one, then the next position depends on start x plus digit distance. Then we know that the column follows. And this can be start x plus twice, plus digit distance plus something else, plus a column distance, plus column distance. And we can, of course, even do this. X, we can give this a variable name x. X is at first just the starting x. And then we just increment it to our needs. For example, here we say x is incremented by the digit distance. And then after the second digit, we say x is incremented by the column distance. This might be the solution for the awkward positioning of the columns. So if we do column distance here, and let's say column distance is just 50, it's much smaller than the digit distance, then the column should be placed closer. And then we can reuse that x position. Then we can increment it again here, plus equals, put another column distance because the column also needs space on the other side. That's where we position this x. Then position another x here. X plus equals column distance. And then x plus equals of course digit distance needs to be used here. Then another digit, then another digit distance, and then comes a colon. No, wait. We have printed a colon here. Then we give this a colon distance. After that, we print a digit that requires a digit distance. Then we print another digit that requires another digit distance. Then we print a colon. Somehow I think that this needs another colon distance here. And then let's just see how that looks like so far, if it even makes sense. Of course, there's an error. Colon distance. There was a typo in colon distance. But now it should be solved. Yeah, that's completely flawed. Completely broken now. So we do digit distance, colon distance, digit distance, colon distance. No, this needs another digit distance. We first start at the starting position. then we draw a digit, then we increment by the digit distance, then we draw another digit, then we increment by the colon distance here. Before the colon, we need to increment by the colon distance. And after the colon, we also need to increment by the colon distance, I would say. Digit. Okay, that is the result that we had before. Now here we need to reduce the distance for the colon. Draw colon, colon distance. Yeah, and the colon distance is of course way too small. It should be more like 90 maybe. That's also too small. 100. 110. Okay. And then before a digit, after a colon, before a digit, we use the colon distance as well. Okay. I'm just missing it somewhere. Here's a colon distance, then we draw a colon, and then after that we also need to use the colon distance. And this looks okay to me. Yes, let's just keep it that way. Now we can reduce the width again a bit to 1000 or 1040. And that's a digital clock display. Now we just need to make the clock update according to the current time. So we fetch the current time. We're currently just printing the time as a time string. However, that does not really help us much. We should get a real time structure using local time. Let's have a look here. Local time converts the calendar time to a broken down time representation expressed relative to the user specified time zone. So we get the seconds and minutes and hours, I think. We just need this time p pointer, which is a time t value. Okay, so we are already getting the current time here. Then we don't need to print it via ctime. We don't need to print out anything here. We get the current time. No. We get the current time in the loop, of course. We get the current time. And then we use local time on that current time to get a struct tm pointer. Struct tm pointer current local time is equal to local time of the current time, and then we draw the time given the current local time. Do we need to free it somewhere? No. And when we draw the time based on the current local time, or rather, no, let's keep the API simple. Let's keep our part of the job simple. We want to draw the time, and we receive as input hours, minutes, and seconds. And first, we print the hours value. The first digit is hours modulo 10, probably. That would be, no, hours modulo, wait. We have hours that go from 0 to 12 or 24, depending on where you live. So the hours, the first, how do we get the hours value of the first digit, maybe hours divided by 24. This gives you well, the value after the digit is probably hours modulo 24, and the value before the digit is probably hours divided by 24. So this is the factor, this is the remainder. I'm just guessing. Then same for minutes, divided by 60, and then minutes No, it's decimal places, of course. So we need to do hours divided by 10 and hours modulo 10. Same for minutes. Here we need to do minutes divided by 10 and minutes modulo 10. And same for the seconds, where we need to do seconds divided by 10 and seconds modulo 10. This doesn't work because, of course, we're not passing these values into our draw time function yet. We need to pass in tm hours, tm minutes, and tm seconds. Let's have a look. If we open user include time.h, there should be the struct tm somewhere. Is it defined here anywhere? Or we can probably find something out about this tm struct in a different way. We can try to do the following. Wait, there's a hack for that. Let's do an echo of time.h and we pass that into the C compiler preprocessor, and then we pipe that into less. Oh no, we grab for struct tm. There's nothing in here. Right, okay, that probably means that the functions are defined somewhere else. Time.h struct tm. Echo time. No, of course, that's what have I been doing? Of course, need to pass an include statement into the preprocessor. It needs to be, well, let's see. Now, if I search for the struct tm, is it defined anywhere? Struct tm. There it is. Let's go into less and search for it there. Right, there it is. Okay, those are the fields. So tm sec min hour. That's good. So that's exactly what we need. Tm sec, tm hour, tm hour, tm min, and tm arrow, tm sec. And now there's still an error, tm is undeclared. Why is it undeclared? I'm literally assigning it up here. Current local time, current time. Let's have a closer look at the difference. Time.h needs to be imported. I have already included it. Error tm undeclared. First use in this function. Maybe I shouldn't name. Of course, the variable is called current local time, not tm. And let's see. Still wrong. This is the episode of wrongness. Expected parenthesis before semicolon token in line 96. Or was it 46? 49, line 49 maybe. 49. No. 96. I don't know. Hours divided by 10. I missed something there. Let's go up and search. Of course. I messed up a parenthesis here. Oh. Segmentation fault. Segmentation fault, but that's fine. So now we can just replace the draw time with the current local time thing and see what... Wait, I think I know what. Yeah, we need to pass the time value as a pointer, as you can see. So that's probably what I'm messing up, because currently we're just passing in some integer and then it's looking up a wrong memory address. And guys, this is finally a working clock. We can just make it blink or do something, but actually it's fine. It's fine, isn't it? So, 3 in the morning, 5 minutes after that, 17 seconds, 18 seconds, 19 seconds. This is a perfectly working digital clock in C. Maybe one nice thing that we could do that also real digital clocks do is make the columns blink. So currently we're always drawing the columns here in draw column, and we could draw them at a specific with a specific color, depending on the hours, minutes, and seconds value. So here we could give this a seconds question, seconds modulo 2. Is it divisible by 2? Question mark. If yes, then the color is on color, else it's off color. Or maybe even better, let's just pass the seconds value into the draw column function, because we determine the color values up here inside the draw column function anyways. So draw column, and then we draw the column here. We pass in the seconds value. This is also aligned with the other functions then. And do we draw another column? No, just 2. And then we pass in seconds here. And if, yeah, we just check seconds modulo 2. So every second, we draw an on color and then an off color. And same thing for the other column as well. Seconds modulo 2, question mark, on color, else off color. So now now it's always on odd seconds numbers. I don't like that. But why is that the case? Wait, if we save this, doesn't matter. I'll just reverse the logic here. Off color, on color, on color. If seconds modulo 2 is 0, that means seconds is divisible by 2, and this by 2. Then in that case, the result will be 0, and that means it will jump into the second part of the ternary operation. Yeah, and that's why this was inversed. Off color here. Let's go. That's it, guys. A working digital clock in C using Raylib. I hope you enjoyed it. Have a look at the no-nonsense C programming course linked in the description down below. Teaches you real practical C programming that enables you to create real projects in pure C such as this one. You can make anything happen that you want if you just put your mind to it. And the course really gets you to that level where you can make real stuff happen, not just boring printouts, not boring academic lessons, not weird linked list implementations that you're never going to use, practical programs such as this one. All right. I hope you enjoyed it. If you did, then see you next time. Bye-bye.